Have you ever quietly wondered how long you could actually survive on another planet? Not in a fancy spaceship, just you, in your normal clothes. The answer is usually not very long, but the way you would cease to be is a fascinating and deeply strange tour of our solar system's most hostile and bizarre environments. Let's begin our tour with a place where survival is measured in the blink of an eye. Our first stop is, of course, the great furnace at the center of it all, the sun. Surviving on the sun is a bit like talking about going for a swim in an active volcano. The very concept is a fun kind of absurd. The sun is not a solid object with a surface you can stand on. It is a star, a colossal, churning, incandescent ball of plasma, a continuous nuclear explosion 1,000,000 times the size of the Earth. So your survival time is, to be generous, less than 1 second. It would be an instantaneous, dramatic, and frankly, very thorough end. But let's just quietly appreciate the sheer overwhelming force we're talking about here. The visible surface of the sun that we see from Earth is called the photosphere. The temperature here is about 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit. At this temperature, the very idea of solid matter is a joke. Your body, your clothes, the watch on your wrist, every single thing that makes up you would be instantly vaporized. You wouldn't be burned, you would be turned directly into a puff of your constituent atoms. These atoms would then be immediately stripped of their electrons by the intense heat, turning your physical form into a small, insignificant, and very brief cloud of plasma, which would then simply join the sun's own turbulent atmosphere. But even if you could, somehow, through some form of cosmic magic, withstand that incredible temperature for a moment, the sun has plenty of other ways to end your journey. Let's talk about the gravity. The gravity on the surface of the sun is about 28 times stronger than the gravity on Earth. If you weigh, say, 150 pounds, or about 70 kilograms on Earth, you would, for a fleeting fraction of a second on the sun, weigh over 4,000 pounds, or nearly 2 metric tons. You would be instantly and completely crushed by your own immense weight. Your bones, which are incredibly strong, would turn to dust under the strain before they even had a chance to be vaporized. It's a quiet and absolute kind of pressure. The sun doesn't just want to unmake you with heat. It wants to flatten you with its sheer immense mass. And then there's the light. The gentle sunlight we experience on a bright summer day is a filtered, diluted, and very distant version of the real thing. The sunlight on the surface of the sun itself is a force of incredible destructive power. The intensity of the light is so high that it would be like having billions of the world's most powerful laser beams focused on every square inch of your body at the same time. The sheer energy of the photons would blast your atoms apart. It would be a profoundly, unimaginably bright and violent end. It's not just hot, it's a physical bombardment of pure light. And if the heat, the gravity, and the light weren't enough, there is the magnetism. The sun is a chaotic, churning tangle of colossal magnetic fields. These fields are constantly twisting, snapping, and reconfiguring themselves, creating solar flares that release the energy of millions of hydrogen bombs at once, and coronal mass ejections that throw billions of tons of plasma out into the solar system. To be on the surface of the sun would be to exist in the middle of the most violent and energetic electrical storm in the entire solar system. You wouldn't just be vaporized, you would be vaporized while being subjected to magnetic forces so powerful they could tear atoms apart. So, survival on the sun is a quiet non-starter. It is the great furnace, the engine of our solar system, a place of pure, creative, and utterly, completely unsurvivable power. Its purpose is not to be a home, but to provide the warmth and light that allows for homes to exist elsewhere. It is a beautiful, quiet, and deeply humbling reminder of the sheer scale of the forces that govern our cosmic neighborhood. It's the ultimate look but don't touch exhibit in our Museum of Worlds. And with that rather dramatic starting point, let's take our first step outwards on our tour. We're heading for the closest, fastest, and most thermally abused of all the planets. Our next stop is the small, scorched, and airless world of Mercury. Being the closest planet to the Sun, you might think survival on Mercury would be just as instantaneous as on the Sun itself. But Mercury is a world of strange and quiet quirks, and these quirks make the question of survival a little more interesting. Your survival time here, under the absolute best case, most carefully chosen scenario, would be about 2 minutes, a veritable eternity compared to the Sun. So what is the ultimate cause of your demise on Mercury? What is the final non-negotiable problem that those 2 minutes run up against? The answer is the atmosphere, or rather the almost complete and total lack of one. Mercury is a barren, rocky world with only a very, very thin and tenuous exosphere. This isn't a real atmosphere in the sense that we think of one. It's just a collection of a few stray atoms, mostly oxygen, sodium, and hydrogen, that have been kicked up from the planet's surface by the solar wind and micrometeoroid impacts. It is, for all intents and purposes, a hard vacuum. So, the moment you arrive on Mercury, you would be exposed to the vacuum of space. As we've explored before, this is not a pleasant experience. The first thing that would happen is that all the air in your lungs would be instantly and violently ripped out. If you tried to be clever and hold your breath, the expanding air would rupture your lungs, which would be a fatal injury in itself. Without external pressure to hold you together, the moisture on your tongue, in your nose, and on the surface of your eyes would instantly boil away into the vacuum. And after about 10 to 15 seconds of this deeply unpleasant and disorienting experience, you would lose consciousness due to hypoxia, a simple lack of oxygen to the brain. From that point on, you would be unaware of your surroundings. Your brain, starved of oxygen, would cease to function completely after about another minute and a half. So the ultimate, quiet cause of death on Mercury is simple suffocation. But just because you have about 2 minutes of life doesn't mean those 2 minutes would be in any way comfortable. Far from it. Mercury is a world of the most brutal temperature extremes in the entire solar system. And which one of these extremes would get you depends entirely on where you happen to be standing. Let's imagine, for a moment, that your arrival on Mercury is a little clumsy and you find yourself on the day side of the planet. This side of the planet is a true cosmic oven. With no atmosphere to provide any protection or to scatter the sunlight, the surface is subjected to the raw, unfiltered, and incredibly intense radiation of the nearby sun. The sun in the sky of Mercury would appear about 2.5 times larger and over 6 times brighter than it does from Earth. The surface temperature on the day side of Mercury soars to a blistering 430 degrees Celsius, or about 800 degrees Fahrenheit. That is more than hot enough to melt lead. In this environment, you would be simultaneously suffocating and being roasted alive. Your clothes would likely smolder and burst into flames in a matter of seconds. Your skin would suffer catastrophic third-degree burns all over your body. The ground beneath your feet would be so hot it would sear through the soles of your shoes. It would be a very quick, very painful, and very dramatic end. Your 2-minute window of consciousness from suffocation would be cut drastically short, as you were, for all intents and purposes, cooked. So, what if you were clever? What if you decided to arrive on the night side of Mercury instead, to avoid the heat? This, it turns out, is an equally bad, if slightly less fiery, idea. Mercury has an incredibly long and slow rotation. A single night on Mercury lasts for about 88 Earth days. And with no atmosphere to hold on to any of the heat that was built up during the long day, the night side becomes one of the coldest places in the entire solar system. On the dark side of Mercury, the temperature plunges to a shocking, profoundly cold -180 degrees Celsius, or about -290 degrees Fahrenheit. This is a cold so deep it is far beyond anything we ever experience on Earth. At this temperature, you would freeze solid almost instantly. The water in your cells would turn to sharp ice crystals, destroying them from the inside out. Your 2-minute window of consciousness from suffocation would again be largely irrelevant, because you would become a frozen, brittle statue long before your brain ever ran out of oxygen. It's a quiet, clean, and very, very cold end. So, our thought experiment seems to have a problem. The day side roasts you, the night side freezes you. Where then does our 2-minute survival time come from? It comes from a very specific, very narrow, and constantly moving location on the planet's surface. This is the Terminator line, the beautiful, quiet boundary between the scorching day and the frigid night. Here, at sunrise or sunset, the angle of the sun is so low that the temperature on the surface would be, for a brief and fleeting time, almost comfortable. There would be a sliver of land where the temperature might be a pleasant 20 degrees Celsius, or about 70 degrees Fahrenheit. If you were able to place yourself perfectly within this moving twilight zone, you could avoid being either instantly cooked or instantly frozen. In this one strange, fleeting place, you could stand for a moment and appreciate the bizarre landscape of Mercury. You would see the incredibly long shadows cast by the crater rims. You would see a sky that is permanently black, even during the day, with the stars always visible. And you would be able to stand there in a bizarrely pleasant temperature for the full 2 minutes it takes for you to quietly suffocate from the complete and total lack of air. It is the most comfortable and the most lethal place on the entire planet. From the quiet, airless world of Mercury and its strange Terminator zone, let's now continue our journey outwards to the second planet from the Sun. This is Venus. And if Mercury was a world of quiet, simple hostility, Venus is a world of loud, complex, and almost comically over-the-top lethality. It is often called Earth's evil twin, and I think that is the perfect description. It is, without any serious competition, the single most inhospitable planetary surface in our entire solar system. Your survival time here is less than 1 second. And in that one fleeting second before your existence is completely and totally extinguished, you would have the unique experience of being simultaneously crushed, melted, dissolved in acid, and suffocated, all at the same time. Venus, it seems, is not a planet that does things by halves. It is a world that wants you gone, and it wants you gone immediately. Let's start with the first thing that would get you, the crushing atmospheric pressure. We often think of Venus as being similar in size and mass to Earth, and it is. They are planetary siblings, but their atmospheres could not be more different. The air on Venus is incredibly, incredibly thick and heavy. The atmospheric pressure on the surface of Venus is over 92 times greater than the sea level pressure on Earth. Let's try to put that into a quiet human perspective, because a number like 92 times is hard to grasp. Experiencing that kind of pressure would be the equivalent of diving a full kilometer, or about 3,300 feet, down into our own ocean. No human can survive that kind of pressure. The immense weight of the water would crush our bodies instantly. The deepest a military submarine can go is only about half that depth. The pressure on the surface of Venus is so great that it is at the very edge of what our most advanced deep-sea robotic submersibles can withstand. You would be, in the most literal sense, imploded by the weight of the air around you. This would all happen in a fraction of a second. It is a quiet, powerful, and absolute mechanical end. But even if you could somehow, through some form of impossible magic, survive being crushed, Venus has other, equally unpleasant and equally quick ways to kill you. Let's imagine for a moment that you have a magical suit made of an uncrushable material. You would still have to deal with the heat, and the heat on Venus is a special planetary scale kind of hell. This is the famous case of a runaway greenhouse effect. Venus's atmosphere, as we know, is about 96% carbon dioxide, which is a very powerful greenhouse gas. This thick, planetary blanket of CO2 is incredibly efficient at trapping the sun's heat. The sunlight comes in and warms the planet's surface, but this thick, soupy atmosphere does not let the infrared heat radiate back out into space. The result is a surface temperature that is a steady, uniform, and mind-boggling 465 degrees Celsius, or about 870 degrees Fahrenheit. This is the hottest planetary surface in the solar system, far hotter than Mercury, even though Venus is about twice as far from the Sun. It is hotter than the inside of a self-cleaning oven. At this temperature, the metals lead, tin, and zinc all exist as liquids. The very rocks on the surface of Venus are thought to glow with a dull reddish light from their own intense heat. So, in your magical, uncrushable suit, you would be instantly and completely cooked. Your body would be flash heated to a temperature far beyond what any biological process can possibly withstand. You would be, for all intents and purposes, incinerated in less than a second. It's a quiet, dry, and incredibly efficient kind of lethality. It's a stark and powerful lesson in the delicate balance of a planet's climate. Venus is a quiet, terrifying postcard from a world where the greenhouse effect went completely, catastrophically wrong. But let's keep playing our strange and slightly morbid thought experiment. What if your magical suit was also perfectly refrigerated? What if you could somehow withstand both the crushing pressure and the incinerating heat? You would still have to deal with the air itself. The atmosphere of Venus is not just hot and heavy, it is also incredibly toxic and corrosive. The air is almost pure carbon dioxide, so you would, of course, suffocate instantly from a lack of oxygen. But it gets worse. The thick, pale yellow clouds that perpetually shroud the entire planet are not made of water vapor like the clouds on Earth. They are made of droplets of corrosive, concentrated sulfuric acid. It literally rains acid on Venus. Now, the surface itself is so hot that this acid rain actually evaporates long before it ever hits the ground, a phenomenon called virga. But this means that the lower atmosphere is filled with a permanent, hot, acidic haze. Breathing this air would be the equivalent of breathing in a cloud of industrial-grade battery acid. It would destroy your lungs in a fraction of a second. And even if you didn't breathe it, just being exposed to it would be a problem. The first Soviet probes that successfully landed on Venus, the Venera landers, were incredible feats of engineering. They were built like little spherical bank vaults to withstand the pressure and heat. But even they only survived for a short time on the surface, for about an hour or two, before the combined effects of the heat, the pressure, and the corrosive atmosphere destroyed them completely. So there is no quiet corner, no gentle loophole, no survivable terminator zone on the surface of Venus. It is a world that is, in every conceivable way, the perfect and complete opposite of habitable. It is a quiet, beautiful, and deeply violent world, a true vision of hell in our own solar system. So, after visiting the strange, airless world of Mercury and the truly over-the-top hellscape of Venus, it feels like a good time for a quiet and much-needed interlude. Let's bring our journey home. Let's make a stop at the third planet from the Sun, a small, rocky, and wonderfully water-rich world known as Earth. Your survival time here? Well, with a little bit of good fortune and some sensible life choices, about 80 years, give or take. It's a funny thing to include our own planet on a tour of hostile worlds. In a way, it doesn't seem to fit, but I think it's the most important stop of all. Because in quietly appreciating all the spectacular and efficient ways the other planets would kill you, we can gain a much deeper and more profound appreciation for the quiet, beautiful, and almost miraculous combination of factors that make our own world a perfect, gentle, and lifelong haven for us. Let's just quietly consider some of the things that we take for granted every single moment of our lives. We have an atmosphere, and it is the perfect atmosphere. It is thick enough to provide us with the right amount of air pressure for our lungs to work efficiently, but not so thick that it crushes us. It contains a generous and wonderfully stable 21% free oxygen, a highly reactive and wonderful gas that powers our warm-blooded metabolism. This atmosphere also contains just the right amount of greenhouse gases, like water vapor and carbon dioxide, to create a gentle, stable greenhouse effect, keeping our planet at a comfortable average temperature of about 15 degrees Celsius, not too hot and not too cold. And high up in this atmosphere, there is a delicate layer of ozone that acts as a perfect shield, absorbing the most harmful ultraviolet radiation from the sun. But our planet's defenses don't stop with the atmosphere. We also have a powerful, internally generated magnetic field. This quiet, invisible force field, the magnetosphere, is generated by the churning of the liquid iron in our planet's outer core, and it is our primary shield against the harsh radiation of space. It deflects the most harmful, high-energy particles of the solar wind and the most energetic galactic cosmic rays, preventing them from reaching the surface and from stripping away our precious atmosphere over time. It is this quiet, invisible guardian that keeps our world safe and wet. And of course, there is the water. Our planet's surface is over 70% covered in vast, deep oceans of liquid water. This is the essential solvent for all life as we know it. We live on a world that is, by cosmic standards, a water paradise, a rare and beautiful blue marble. We also have a surprisingly large moon, whose gravity has stabilized our planet's axial tilt for billions of years, giving us our predictable, calm seasons and preventing the kind of chaotic climate swings that might make complex life impossible. And we have active plate tectonics, a quiet, planetary-scale recycling program that regulates our climate over geological time, acting as a global thermostat. It is a long, long list of lucky circumstances, a series of cosmic lotteries that we seem to have won over and over again. It's a quiet testament to the fact that a habitable world is not the default state of a planet. It is a rare, precious, and perhaps incredibly improbable exception. The story of survival in our solar system is, for the most part, a story of impossibility. Earth is the one, quiet, beautiful chapter in that story that is all about possibility. It is the home that allows us to even quietly contemplate the hostility of its neighbors. And with that quiet, appreciative thought in our minds, let's leave our beautiful blue home once more and continue our journey outwards. We are now heading to the fourth planet from the Sun, a world that is, in many ways, the most tantalizing, the most famous, and the most heartbreaking of all our neighbors. We are heading for Mars. Mars has long been the great hope in our search for life beyond Earth. It is a world that we have studied in incredible detail. We have sent orbiters, landers, and rovers there. And it is, in many ways, the most Earth-like world in our solar system. But Earth-like is a very, very relative term. And if you were to stand on its rusty, dusty surface without a spacesuit, your survival time would be very, very short. Just like on Mercury, you would last about 2 minutes. And once again, the primary and inescapable cause of your demise would be simple, quiet suffocation. The Martian atmosphere is incredibly thin. It is less than 1% the density of Earth's. It is a mere whisper of an atmosphere. Standing on the surface of Mars would feel like being at an altitude of over 30 kilometers, or about 100,000 feet on Earth, far higher than any mountain, in the near vacuum of the stratosphere. And the composition of this thin air is almost entirely carbon dioxide, about 96% of it, with only a tiny, useless trace amount of oxygen. So the moment you arrived, you would be in an unbreathable environment. You would try to take a breath, but the air is so thin and so devoid of oxygen that it would do you no good at all. The story would be the same as on Mercury. You would have about 10 to 15 seconds of useful consciousness before you passed out from hypoxia, followed by a couple of minutes before full and irreversible brain death. The quiet, cold, red desert of Mars would be the last thing you ever saw. But just as with Mercury, suffocation is not the only problem that Mars has in store for you. The incredibly thin atmosphere creates another, much stranger and much more immediate physical challenge. This is the bizarre and deeply unsettling phenomenon of ebulism. We talked about how the liquids on your tongue and in your eyes would boil in the pure vacuum of Mercury. Well, the atmosphere on Mars, while not a pure vacuum, is so incredibly thin that its pressure is below a critical threshold known as the Armstrong limit. This is the point at which the atmospheric pressure is so low that water boils at normal human body temperature, which is about 37 degrees Celsius. This has some rather grim consequences for our thought experiment. The moment you were exposed to the thin Martian air, the water in your soft tissues, the moisture in your skin, in your muscles, in your organs, and even in your blood would begin to boil. It would not be a hot boiling caused by heat, but a cold boiling caused by the simple lack of external pressure to keep the water in its liquid state. This process of ebulism would cause your body to swell up to a grotesque size, perhaps twice its normal volume. The formation of these water vapor bubbles throughout your body would cause massive and irreversible tissue damage. It is a quiet, strange, and deeply unpleasant way to go. So, in your first few seconds of consciousness on Mars, you would be experiencing both the desperate, breathless feeling of suffocation and the bizarre swelling sensation of your own body boiling from the inside out. And then, of course, there is the cold. Mars is a frigid, frozen desert. While the temperature at the equator on a sunny summer day can sometimes briefly and pleasantly climb to about 20 degrees Celsius or 70 degrees Fahrenheit, this is a rare exception. The average temperature for the planet as a whole is a brutal minus 60 degrees Celsius or minus 80 degrees Fahrenheit. And at night or at the poles, it can plummet to well below minus 100 Celsius. So, in almost any location, at almost any time on Mars, you would be simultaneously suffocating, boiling, and flash freezing, all at the same time. It is a world that is hostile in a quiet, complex, and multi-layered way. But the real quiet tragedy of Mars is not what it is today, but what it once was. As we've explored, the evidence from our robotic rovers is now overwhelming. Billions of years ago, Mars was a very different world. It had a much thicker, warmer atmosphere, one that was capable of supporting vast, stable bodies of liquid water on its surface. It had rivers, it had lakes, it had perhaps even a great northern ocean. It was, for a time, a true second habitable world in our solar system, a world that had all the necessary ingredients for life to begin. And that is what makes Mars so heartbreakingly tantalizing. It is not a world that was always hostile. It is a world that became hostile. It is a quiet, planetary-scale fossil. It is a story of a world that lost its chance at life. Its thin, cold, and unbreathable atmosphere is a ghostly remnant of a once thicker, warmer, and more protective blanket. It is a quiet, red reminder of just how precious, and perhaps how fragile, a planetary biosphere can be. Mars is not a hellscape like Venus. It is a paradise lost. And that, I think, is an even more poignant and quietly sad story. Now we must leave the inner rocky worlds behind. Our tour of quiet, hostile environments is about to take another great leap outwards, past the asteroid belt, into the vast, cold, and dark realm of the giant planets. And here, the question of survival time becomes a little more abstract, but the answer is always the same: instantaneous and spectacular. We have completed our quiet and rather lethal tour of the inner rocky worlds. We have seen that survival on these planets is measured in minutes, or, in the case of Venus, in milliseconds. Now we must take a much longer journey outwards, past the vast, lonely expanse of the asteroid belt, into the deep, cold, and dark realm of the giant planets. And here, the question of survival time becomes a little more abstract, but the answer is always the same: instantaneous, complete, and on a scale that is almost too large to comprehend. We begin our tour of the outer void with the undisputed king of our solar system, the fifth planet from the Sun, the colossal and magnificent Jupiter. To talk about surviving on Jupiter is a quiet contradiction in terms, because there is nothing to survive on. Jupiter is a gas giant. It has no solid surface to stand on, no ground beneath your feet. If you were to be dropped into its atmosphere, your journey would be a one-way and very, very brief trip down into a bottomless, crushing, and stormy abyss. Your survival time would, without any question, be less than 1 second. Let's just quietly imagine that final spectacular journey. Your first problem would be the incredible turbulence and the ferocious winds. The beautiful, swirling, pastel-colored cloud bands that we see in pictures from our telescopes are actually continent-sized jet streams and colossal storm systems moving at hundreds of kilometers per hour. You would be caught in a planetary-scale hurricane of almost unimaginable power, tossed around in the upper cloud decks. These highest clouds are not made of water vapor. They are made of frigid, sharp, and toxic crystals of ammonia ice, whipping past you in a hypersonic blizzard. But you wouldn't have time to appreciate the strangeness of an ammonia blizzard. As you were tossed about by the incredible winds, you would be descending deeper into the atmosphere. And as you descended, the pressure and the temperature would begin to rise at a staggering, relentless rate. The atmosphere of Jupiter is mostly hydrogen and helium, the lightest elements in the universe. But as you go deeper, the sheer weight of all the gas above you begins to do strange things. Within just a few hundred kilometers of the cloud tops, you would reach a point where the pressure is so immense that the hydrogen gas itself is compressed until it is no longer a gas. It becomes a strange, soupy liquid. A few thousand kilometers deeper still, the pressure becomes millions of times greater than the sea level pressure on Earth. And at this point, the hydrogen is squeezed so tightly that its electrons are no longer bound to their protons. They can flow freely, like the electrons in a piece of metal. This is a bizarre state of matter known as liquid metallic hydrogen. Deep inside Jupiter, there is a vast planet-spanning ocean of this strange conductive liquid metal. Any spacecraft, and certainly any human body, would be instantly and completely crushed by the immense pressure long before it reached this deep part of the planet. Your physical form would be squeezed out of existence in a fraction of a second. The quiet, gentle clouds of Jupiter that we admire from afar are just the serene surface of an incredibly violent and powerful world of unimaginable pressure. And even this is not the first thing that would get you. Even before you had a chance to be crushed by the pressure or torn apart by the storms, you would have to contend with another, even more insidious and completely invisible threat. This is the danger of Jupiter's radiation belts. As we've discussed in other quiet stories, Jupiter has the most powerful magnetic field of any planet in our solar system. It is a colossal magnetic bubble, a magnetosphere, that is nearly 20,000 times stronger than Earth's. It is so enormous that if you could see it from Earth, it would appear larger in our night sky than the full moon. And this incredible magnetic field has trapped a huge number of high-energy charged particles. These particles come mostly from the solar wind, but a significant and very powerful portion of them are particles of sulfur and oxygen that have been erupted from the hundreds of active volcanoes on Jupiter's moon Io. These trapped particles form a set of radiation belts around Jupiter that are so incredibly intense, they are one of the single most dangerous places in the entire solar system. The radiation dose inside these belts is thousands upon thousands of times higher than the lethal dose for a human being. An unshielded person traveling through the heart of these belts would receive a fatal dose of radiation in a matter of seconds. The high-energy particles would shred your DNA and destroy your cells, causing a rapid and catastrophic failure of your central nervous system. It would be a quiet, invisible, and very, very quick end. Even our robotic probes that we send to Jupiter, like the Juno spacecraft that is in orbit there right now, have to be heavily shielded. They are built like little flying bank vaults, with their sensitive electronics encased in a thick titanium shell, just to survive the constant high-energy bombardment. And even with this shielding, their orbits are carefully designed to be long, looping polar paths that spend as little time as possible in the most intense parts of these radiation belts. So, for our quiet thought experiment, your journey to Jupiter would be over long before you ever reach the planet itself. You would be quietly and invisibly dispatched by the silent, ghostly guardian of radiation that surrounds the king of the planets. Jupiter is a world that is hostile on every conceivable level. From its powerful radiation to its stormy atmosphere, from its complete lack of a surface to its deep, crushing pressures. It is a beautiful, magnificent, and deeply, deeply unsurvivable place. From the king of the planets, we now drift outwards to the sixth planet from the Sun, the beautiful, ethereal, and equally deadly world of Saturn. Just like Jupiter, Saturn is a gas giant. It has no solid surface to stand on, and so your survival time here would, once again, be less than 1 second. The story of your final moments would be very, very similar to the one at Jupiter, just with a slightly different, and in some ways, even more extreme and bizarre flavor. If you were to descend into Saturn's atmosphere, you would first be greeted by its famous and almost unbelievably fast winds. The equatorial jet stream on Saturn is one of the fastest in the entire solar system, with winds that have been clocked at over 1,800 kilometers per hour, or about 1,100 miles per hour. This is significantly faster than the winds on Jupiter. You would be caught in a hypersonic, planet-spanning hurricane of incredible power, tossed about in the upper, hazy, golden-yellow cloud decks of ammonia ice. As you descended deeper, you would pass through clouds of water ice, and just as with Jupiter, the pressure and the temperature would continue to rise at a relentless and unforgiving rate. The hydrogen gas would be compressed into a liquid, and then, deeper still, into a strange state of liquid metallic hydrogen. And the crushing pressure of these deep layers would once again be the final, definitive, and very quick end to your journey. Saturn also has its own set of powerful radiation belts trapped within its magnetic field. They are not quite as intense as Jupiter's terrifying belts, but they are still more than powerful enough to deliver a lethal dose of radiation to an unshielded human in a very short amount of time. And what about those beautiful, iconic rings? While they look solid and serene from a distance, they are, as we know, made of countless individual particles of almost pure water ice, ranging in size from tiny dust grains to boulders as large as a house. And these particles are all orbiting Saturn at incredible speeds, thousands of kilometers per hour. Flying through the main rings of Saturn would be the equivalent of flying through a high-speed, perpetual blizzard of icy shrapnel. Any spacecraft, and certainly any human body, would be shredded to pieces in a fraction of a second. They are a beautiful, quiet, and incredibly dangerous celestial buzzsaw. And what about that bizarre hexagonal storm at Saturn's North Pole? This is a stable, six-sided jet stream, a weather pattern so large that each of its six sides is wider than our entire planet. The winds inside this storm are ferocious, and at its center is a swirling, hurricane-like vortex. It is a beautiful, deeply mysterious, and perfectly geometric storm. It's a quiet spectacle to behold from afar, but to be inside it would be to be caught in a storm system of almost unimaginable power and scale. Like its larger sibling Jupiter, Saturn is a world of immense, quiet beauty and equally immense, quiet hostility. It is another world designed to be admired from a very, very great distance. Now we must take another long, quiet journey outwards into the deep, cold, and dark suburbs of our solar system. We are heading to the even more mysterious realm of the ice giants. Our first stop is the seventh planet from the Sun, the strange, tilted, blue-green world of Uranus. Once again, as an ice giant, Uranus has no solid surface to stand on. So your survival time here would be, you guessed it, less than 1 second. The story of your descent would be one of incredible, profound cold, and then, finally, crushing pressure. But the details are a little different and a little stranger than what we saw at the gas giants. Uranus, as we've discussed, is the coldest planet in the entire solar system. Its upper atmosphere has a minimum temperature of a frigid -224 degrees Celsius, or just 49 degrees above absolute zero. It is actually colder than Neptune, which is much farther away from the Sun. This is a quiet, ongoing mystery in planetary science, but it's thought that perhaps the colossal impact that knocked the planet on its side also caused it to vent a lot of its primordial internal heat into space. But for our thought experiment, it means that your first experience of Uranus would be one of profound, instantaneous, and absolute cold. As you descended into its thick, hazy, and rather featureless atmosphere of hydrogen, helium, and methane gas, the pressure would once again begin to rise dramatically. But what lies beneath the gassy upper layers of an ice giant is a very strange and different kind of interior. It is not the vast ocean of liquid metallic hydrogen that we find in Jupiter and Saturn. Instead, the mantle of an ice giant is thought to be a hot, dense, and bizarre slushy mixture of water, ammonia, and methane ices. Now, when we say ices in this context, we don't mean the cold, solid stuff you put in a drink. We mean that these molecules are in a strange, fluid-like state, kept from becoming a gas by the immense pressures. The temperature in this icy mantle could be thousands of degrees Celsius, and the pressure would be millions of times that of Earth's atmosphere. Some have called it a super-ionic ocean, a weird state of matter where the water molecules break apart and the oxygen atoms form a crystal lattice while the hydrogen ions flow through it like a liquid. Descending into this strange, hot, slushy, high-pressure ocean would be a very brief and very final journey, ending, as always, in the complete and total destruction of any object from our world.
And now for our final planetary stop on this grand and rather perilous tour. We travel to the 8th and most distant planet in our solar system, the deep blue and incredibly windy world of Neptune. Neptune is the second of our solar system's ice giants, and it is in many ways the twin of Uranus. It is a similar size and it has a similar composition, and just like its sibling, it has no solid surface to stand on. Your survival time here would be, once again, less than a single second. The story of your final moments at Neptune would be a familiar one by now. A descent into a cold, thick atmosphere, followed by a swift and complete crushing by the immense pressures of the strange, icy, super-pressurized interior. But Neptune adds its own unique and violent signature to the experience. As we've mentioned, Neptune is the windiest planet in the entire solar system. Supersonic jet streams, driven by the planet's small but surprisingly potent internal heat source, whip through its upper atmosphere at speeds of over 2,000 kilometers per hour. That's more than 1.5 times the speed of sound. So, your brief final journey into Neptune's atmosphere would be a ride on the most powerful and most violent winds known to humanity. It would be a chaotic and incredibly turbulent end. And like Uranus, Neptune is incredibly cold. Its deep, vibrant blue color, which is much richer than the pale cyan of Uranus, is also a result of the methane gas in its atmosphere. The methane is very good at absorbing red light from the sun and reflecting the blue light back out into space, giving the planet its beautiful azure hue. The quiet beauty of this deep blue world hides an interior of incredible pressure and an atmosphere of almost unimaginable supersonic violence. It is, like all the giant planets, a world designed to be admired from a very, very great distance.
All right, we have completed our tour of the 8 official planets, and we have found them all to be, without exception, spectacularly and efficiently hostile to human life. Our journey from the sun outwards has been a journey of decreasing temperature and, for the most part, increasing strangeness. But our solar system doesn't end with Neptune. Our final chapter takes us into the vast, cold, dark, and deeply mysterious third zone of the solar system, the Kuiper Belt. Here we will visit the dwarf planets, and we will ask our quiet question one last time. Let's travel to the most famous resident of this distant realm, the one-time 9th planet, the king of the Kuiper Belt, Pluto. What would your survival time be on the surface of this small, icy world? Well, we are now back to a world with a solid surface to stand on, so you wouldn't be crushed by immense pressure. But the environment is so extreme in other ways that your survival time would still be incredibly short. Perhaps less than a second, maybe just a single final heartbeat.
The first, the last, and the most overwhelming problem on Pluto is the absolute cold. Pluto orbits the Sun at an average distance of nearly 6 billion kilometers, about 40 times farther away than the Earth is. At this immense distance, the Sun is no longer a life-giving, warming disk in the sky. It is just a very, very bright star, a brilliant point of light that provides about 1,600 times less heat than we receive on Earth. The result is a world locked in a profound, permanent, and almost absolute cold. The surface temperature on Pluto hovers around a frigid minus 230 degrees Celsius, or just about 40 degrees above absolute zero. This is a cold so deep, so fundamental, that it is hard for us to even imagine. At this temperature, you would freeze solid almost instantaneously. The water in your body's cells would turn to sharp ice crystals in a fraction of a second, destroying them from the inside out. There would be no time for suffocation, no time for the other strange effects of the vacuum. There would only be the quiet, instant, and complete cessation of all biological activity. It is a clean and very, very cold end. But the profound and absolute cold on Pluto is only the first of its quiet and efficient forms of lethality. Even if you had a magical suit that could keep you perfectly warm, you would still have to contend with the other problems of this tiny, distant world. Just like on Mercury, Pluto has an atmosphere that is, for all intents and purposes, a vacuum. It does have a very, very thin and tenuous atmosphere, which was a surprise discovery. It is composed mostly of nitrogen gas that has sublimated from the vast nitrogen ice glaciers on its surface, along with traces of methane and carbon monoxide. But this atmosphere is incredibly, incredibly thin, about 100,000 times less dense than Earth's. It provides no breathable oxygen and almost no pressure. So just as on Mars, you would be in an environment where the pressure is well below the Armstrong limit. The moment you arrived, the lack of pressure would cause the liquids in your body to begin to boil, even in the incredible cold. This process of ebullition would cause massive tissue damage. At the same time, you would be unable to breathe. The air is unbreathable, and there's not enough of it to even fill your lungs. So you would have those same quiet 10 to 15 seconds of useful consciousness before you passed out from hypoxia. The suffocation would be the final, definitive end, but the experience would be a strange and deeply unpleasant combination of freezing, boiling, and suffocating, all happening at the exact same time. And Pluto's thin atmosphere is not even a permanent feature. Pluto has a long, very elliptical orbit. As it moves farther and farther away from the Sun on its 248-year journey, its surface gets so cold that its entire atmosphere freezes and falls to the ground as a layer of nitrogen snow. For a large part of its long year, Pluto has no atmosphere at all. It is a world that literally loses its sky, a quiet, beautiful, and incredibly hostile place. But there is one final, strange feature of being on a world like Pluto that would make your last moments very different from being on a larger planet, and that is the incredibly low gravity. Pluto is a very small world, much smaller than our own moon. Its surface gravity is only about 1/15 that of Earth's. This would create a strange, dreamlike, and slightly comical experience. If you weighed 150 pounds on Earth, you would weigh only about 10 pounds on Pluto. You would feel almost completely weightless. A simple step would send you bounding gracefully and slowly across the landscape. A small jump could send you soaring hundreds of feet into the silent black sky, a beautiful slow-motion arc that would take several minutes to complete. It's a quiet and beautiful thought to be able to jump over mountains of hard water ice and across vast plains of frozen nitrogen.
But it would also be a very dangerous environment. The low gravity would make it very difficult to get any traction on the slippery, icy surface. And if you were to fall, you might fall for a very long time. And this low gravity applies to everything, not just you. The landscape of Pluto, as we saw in the stunning images from the New Horizons probe, is a testament to this. We saw colossal mountains of water ice, some as tall as the Rocky Mountains on Earth, that are able to support their own immense weight in the low gravity. We saw vast, smooth glaciers of frozen nitrogen slowly flowing across the surface, driven by the planet's faint internal heat. It is a world that is shaped by the same geological processes as Earth, but with the gravitational volume turned way, way down. It's a quiet, gentle, and deeply frozen world at the very edge of our Sun's influence. And its story is likely the story of most of the other large worlds in the Kuiper Belt.
Our journey into the deep freeze doesn't end with Pluto. There are other known dwarf planets out there, in even more distant, more lonely, and colder orbits. Let's make a brief, quiet stop at one of them, the one that famously dethroned Pluto from its planetary status. Let's visit Eris. Eris is a dwarf planet that is, for the most part, even farther away from the Sun than Pluto. It is roughly the same size as Pluto, but it is about 27% more massive. This means it is made of much denser, rockier material. Its orbit is a long, slow, and very eccentric one, taking about 557 Earth years to circle the Sun once. And its orbit is also highly inclined, meaning it travels far above and below the main plane of the solar system where the other planets live. At its farthest point from the Sun, it is nearly 100 times farther away than the Earth is. The environment here would be even more extreme than on Pluto. The sunlight is even fainter, just a brilliant, distant star. The cold is even more profound, with surface temperatures that likely drop to just 30 degrees above absolute zero. The survival time here would be just as instantaneous as on Pluto. A quiet, frozen end in a place of almost unimaginable cold and darkness. The discovery of Eris in 2005 is what directly led to the Great Planet debate and the eventual reclassification of Pluto a year later. The discovery of a world as massive or even more massive than Pluto in the outer solar system forced astronomers to ask a quiet, difficult, but necessary question. If Pluto was a planet, then is Eris a planet too? And what about the other large objects we were starting to find out there, like Makemake and Haumea? Where do we draw the line? This led to the creation of the formal dwarf planet category, a decision that remains, for many people, a quiet and slightly sad footnote in the history of astronomy. But it was a decision that gave us a much more accurate and interesting picture of our solar system, with its 8 diverse planets and its bustling, populated third zone of icy dwarf worlds.
And so, we have completed our grand and rather lethal tour of the major worlds of our solar system. We have journeyed from the impossible, incandescent fury of the Sun to the scorched and frozen plains of Mercury. We have visited the crushing, melting, acid-filled hellscape of Venus and the cold, thin, boiling, and freezing desert of Mars. We have plunged into the bottomless, stormy, and irradiated depths of the gas and ice giants Jupiter, Saturn, Uranus, and Neptune. And we have ended our journey in the profound, absolute cold of the Kuiper Belt on the surfaces of dwarf planets like Pluto and Eris. Let's take a quiet moment here in this interlude to create a kind of hierarchy of hostility, a quiet summary of our journey. At the absolute bottom of the list, the most spectacularly and efficiently unsurvivable places are the Sun and the 4 giant planets. Survival here is not measured in seconds, but in the instantaneous and complete cessation of your existence. You are either vaporized by heat, crushed by pressure, or irradiated to oblivion. These are not places in a human sense. They are environments of pure, raw, and unforgiving physics. Just a tiny, almost imperceptible step up from that is Venus. While it is a rocky planet with a solid surface you could theoretically stand on, that surface is so hot and the pressure so immense that your survival time is still effectively zero. It is, in many ways, the most unpleasant and personally hostile world of all, an overachiever in the art of being deadly. Then we have a more interesting category, the worlds where you could, in theory, survive for a few brief conscious moments. These are the worlds with little to no atmosphere: Mercury, Mars, and the dwarf planets like Pluto. On these worlds, the immediate and definitive end comes from suffocation, a quiet process that gives you about 2 minutes of unconscious existence before the end. But during those 2 minutes, you would also be experiencing a whole host of other deeply unpleasant things. On Mercury, you would be simultaneously roasted by the sun on one side and flash frozen on the other. On Mars, you would be experiencing the strange, cold boiling of your own body fluids in the thin atmosphere. And on Pluto, you would be turned into a brittle, frozen statue in an instant. They are, in their own unique and quiet ways, all equally and completely unforgiving. And this entire, quiet, hostile tour brings us to a final, profound reflection. It is a reflection on the true meaning of the habitable zone, the Goldilocks zone. We often think of it as a simple question of temperature, of being the right distance from the sun for liquid water to exist on a planet's surface. Earth is in this zone, Mars is on its cold outer edge, and Venus is on its hot inner edge. But our journey has shown us that it is so much more complicated than that. A planet can be in the perfect location and still be a complete and total nightmare. Venus is the perfect example. It is, in many ways, Earth's twin. It is in the right neighborhood. But its thick, toxic atmosphere has turned it into a runaway greenhouse, a world far more hostile than even Mercury. And a planet can be in the perfect location and still lose its chance at life. Mars was once a warm, wet world, a true candidate for a second Genesis in our solar system. But its small size meant it cooled down too quickly, and it lost its protective magnetic field, allowing its atmosphere and its water to be stripped away into space. What our quiet tour of survival has shown us is that a habitable world is not just about being in the right place. It is a delicate and beautiful dance of 1,000 different factors.
It requires the right size to hold on to your atmosphere and your internal heat for billions of years. It requires the right atmosphere to provide the right pressure and a gentle, stable greenhouse effect. It requires a powerful, internally generated magnetic field to provide a constant shield against the harsh radiation of space. It requires a stable orbit and a stable, long-lived star. And it requires 1,000 other lucky coincidences that we are only just beginning to understand. From the presence of a large, stabilizing moon, to the existence of active plate tectonics to regulate the climate over geological time. The quiet, humbling truth that our journey has revealed is that the universe is not made for us. Hostility is the default state of a planet. Habitability is the rare, precious, and perhaps almost miraculous exception. Our gentle, blue and white world is not the norm. It is the cosmic jackpot, a quiet, perfect, and perhaps incredibly lonely oasis of calm in a very large and very hostile desert. And with that quiet, appreciative thought, we will conclude this long tour of our solar system and rest here for a while in the peaceful, life-giving, and perfectly calibrated environment of our own gentle and wonderfully hospitable home.
We have seen the hostility of our neighbors, and in doing so, we have come to a deeper and more profound understanding of the quiet miracle of our own existence. There is, it turns out, no place like home. And so, we have come to the end of our grand and rather perilous tour of the solar system. We have asked a simple, if slightly morbid, question: how long would you survive? And the answer, for every world other than our own, has been a resounding, not long at all. We have been crushed, vaporized, irradiated, roasted, frozen, and dissolved in acid. But the purpose of this quiet journey was not to catalog the many ways the universe can kill you. The purpose was to appreciate the many, many ways our own planet keeps us alive. The hostility of other worlds is not a source of fear, but a quiet, powerful reason to cherish the gentle and perfectly balanced environment of our own home. The story of our solar system is the story of how incredibly, almost impossibly, lucky we are to have the Earth. So, as you drift off to sleep tonight, let your mind be at peace. Think of the quiet, thin blue line of our atmosphere, our precious shield. Think of the vast, deep, liquid oceans. Think of the gentle, constant pull of our gravity. And in the quiet, comfortable safety of your own bed, on this perfect, gentle world, I hope you find a deep and wonderfully restful sleep.